Imagine stepping into your car, completely trusting that every component, every wire, every piece of silicon is diligently working, not just to get you from point A to point B, but to actively protect you.
Yeah.
This unseen safety net, right? A complex orchestration ensuring all those electronic and electrical bits function flawlessly, even when facing, the unpredictable.
Exactly. It really is.
This is a world where precision and foresight aren't just admirable traits. They are, well, they're the fundamental pillars holding up our safety on the road.
Absolutely. It's about building in resilience right from the absolute ground floor. It's anticipating what could potentially go wrong, often in ways you wouldn't initially expect. And then meticulously designing every system to handle those challenges safely.
Often without you even noticing.
Right. Often without you even realizing it's happening.
And today, we're taking a deep dive into that fascinating, intricate world of functional safety for road vehicles. Our focus. A crucial blueprint known as ISO26262-Part Part 5, specifically product development at the hardware level. This standard is the detailed step-by-step guide for how the physical components of your car are designed and built to actively prevent dangerous malfunctions.
Our mission in this deep dive is really to unpack the core activities, the precise objectives, and the profound importance of this particular stage in a vehicle's development lifecycle. We're going to explore how those incredibly abstract safety concepts, like, say, avoiding unintended acceleration, are meticulously transformed into robust, tangible, physical hardware.
Right, actual stuff you could hold.
Exactly. Hardware that's designed from the very first transistor, mind you, to withstand the unpredictable nature of random hardware failures.
So get ready to truly understand the sheer engineering dedication that underpins automotive safety. We'll trace this journey from the initial drawing board through incredibly rigorous testing and right into the detailed world of risk evaluation.
And our guide today, the ISO 26262-Part 5.2018 standard itself.
Let's unpack this. Okay, so when we talk about functional safety in automotive development, there's one diagram that sort of stands above all others as the foundational process, the V model.
Yes, the V.
It's not just some abstract academic concept, is it? It's quite literally the blueprint that guides everything.
Yeah.
For someone who might be familiar with general engineering but may be new to functional safety, how does this V model actually frame product development within the ISO 26262 series?
The V model is indeed a foundational reference process model. It gives you a clear visual representation of the entire product development lifecycle, specifically tailored for these safety-critical systems. Think of it like this.
Okay.
The left side of the V represents the decomposition of requirements. You start with high-level ideas, the big-picture safety goals, and then you systematically break them down into increasingly detailed specifications as you go down the left arm.
Breaking it down. Makes sense.
Then, as you move up the right side of the V, you begin the integration and verification activities. You build the system back up piece by piece, incrementally. And crucially, you validate each level of integration and implementation against its corresponding specification that was defined over on the left side.
So you're constantly checking back.
Exactly. This iterative process ensures thoroughness, traceability, a really key concept, and continuous validation. It guarantees that what you end up building truly meets the original safety intent.
That makes perfect sense. It's like a mirror image. Break it down, build it back up, constantly checking against your plan. So where does product development at the hardware level, our focus today, Part 5, where does that fit into this grand V model? Where does this specific stage pick up?
Product development at the hardware level, ISO 26262-Part 5, it picks up directly from the outputs of product development at the system level, which is Part 4.
Okay, so it follows right on.
Right. It's nestled in that critical middle-lower part of the left side of the V. That's where the overarching system-level design starts to get broken down into its distinct hardware and software components. It's the point where the broad strokes of safety strategy begin to take actual physical form.
And what are the critical inputs that kick off this hardware development phase? What do the hardware engineers actually receive as their marching orders from the system level?
The fundamental directives, the main inputs for the hardware engineers at this stage, are two incredibly important documents. The Technical Safety Concept, or TSC.
TSC, got it.
And the System Safety Requirements, often just called SSRs. These are the high-level concepts and specific requirements that were meticulously defined during that system-level development phase we just mentioned, Part 4. They serve as the absolute starting point for hardware design.
So they define the what and the how.
Pretty much. They clearly specify what the system needs to do to be safe and how that safety will be conceptually achieved, often by outlining various safety mechanisms at a high level.
So this is where the abstract what from the system level truly becomes the concrete how in terms of physical components. That's a huge transformation, isn't it?
Yeah.
Moving from a safety philosophy to an actual circuit board.
Precisely. That's the key transformation. The hardware level takes these overarching system-level safety requirements and technical concepts and translates them into actual, tangible hardware implementations. This is where you specify the physical properties of a chip, the precise interfaces between components, the design of specific safety mechanisms like watchdogs or voltage monitors, all the real-world elements that will make the system safe and robust against failures.
And what are the overarching goals of this hardware development phase then? What's the big picture that ISO26262-Part 5 aims to achieve?
Well, the primary objectives are multifaceted. First, it's about performing all the necessary functional safety activities throughout the specific subphases of hardware development. This includes the meticulous hardware implementation of that technical safety concept we talked about,
Right.
which means embedding safety directly into the physical design of the components. Another key objective is to conduct thorough analyses, really deep analyses of potential hardware faults and their effects, identifying any weaknesses before they can become dangerous.
Finding the problems early.
Exactly. And finally, there's critical coordination with software development to ensure seamless integration. You absolutely cannot have safe hardware with unsafe software or vice versa. They have to work in perfect harmony to close any potential safety gaps.
So it's not just about building the hardware, but building it with safety as the absolute top priority, baked in from day one. Makes perfect sense. Okay, now let's talk about how these hardware safety requirements are actually created.
Yeah.
How are they derived and refined from those higher level concepts? I imagine it's a very precise process.
It is, absolutely. It has to be. Hardware safety requirements are meticulously derived from two primary sources: that technical safety concept, the TSC, and the system architectural design specification. This isn't a casual step. It's a direct, traceable flow down from those higher-level safety objectives.
Traceable. There's that word again.
It's fundamental. Imagine a funnel. The broad safety goals go in at the top, and what comes out are highly specific, actionable hardware requirements.
And what are the specific inputs needed for this phase? You mentioned a few coming from the system level.
Yes. The critical prerequisites from the system level, as laid out in Clause 6.3.1 of the standard, include the technical safety concept, the system architectural design specification, and the initial hardware-software interface, or HSI specification.
HSI, okay.
These documents provide the essential context and directives for the hardware safety requirements to be properly defined. They ensure that the hardware team is building to the exact specifications derived from the overall system safety strategy.
Okay, so once you have those inputs, what actually constitutes a hardware safety requirement? Can you give us some detailed examples of what these requirements actually look like? Because I imagine it's not just don't fail.
You're absolutely right. It's incredibly granular. Hardware safety requirements are comprehensive and cover various facets of component behavior and interaction. Let's break them down with examples directly from the standard to give you a feel for their precision. First, we have requirements related to internal failure control. These are for safety mechanisms designed to manage failures within the hardware element itself. For instance, imagine a requirement for a microcontroller's watchdog timer.
Okay, the watchdog.
Right. It might specify the precise timing interval within which the watchdog must be fed or reset by the microcontroller to prove it's still alive and kicking. It would also detail its detection abilities if the microcontroller freezes or goes off course. This ensures the component can, police itself.
Keep itself in check.
Exactly. Next, there are requirements for external failure control or tolerance. These are for safety mechanisms that control or tolerate failures originating outside the hardware element but affecting it.
Like something coming from another part of the car.
Precisely. A good example here is specifying the required functional behavior for an electronic control unit, an ECU, if an external wire connected to one of its input pins develops an open circuit fault. How should the ECU react to prevent a hazardous situation? Does it ignore the input, go to a default safe value, signal an error? That needs to be defined.
Okay.
Then we have inter-element safety compliance. These requirements and properties are for safety mechanisms that enable compliance with the safety needs of other elements in the system.
So, making sure everything plays nicely together.
Essentially, yes. This could involve, for instance, the specific diagnostic capabilities required for a hardware element to ensure the proper functioning and safety of connected sensors or actuators. It's about ensuring elements communicate safely and maintain the integrity of the overall system function.
Makes sense.
Another critical category is fault detection and signaling. These requirements define safety mechanisms that detect and signal internal or external failures. What's crucial here is that they explicitly include measures to prevent faults from becoming latent.
Latent faults. The hidden ones.
The hidden ones, exactly. A latent fault is essentially a hidden failure that doesn't immediately cause an issue, but could, in combination with another independent fault, lead to a dangerous situation down the line.
So you need to find them.
You absolutely need to find them or mitigate their risk. An example of such a requirement would be specifying the fault reaction time for a hardware safety mechanism. This ensures it aligns with the fault tolerant time interval, or FTTI, meaning the system can transition to a safe state before a hazard actually occurs. It's about ensuring hidden dangers are brought to light and dealt with quickly.
And
finally, there are non-safety mechanism requirements. These are other critical hardware requirements not directly related to safety mechanisms per se, but still vital for overall safety.
Like what?
This includes, for example, requirements for hardware elements to meet specific target values for random hardware failures. We'll get into those metrics later. Or requirements for avoiding undesirable behaviors, like a sensor producing an unstable, noisy output signal rather than a steady, reliable one. It also covers crucial but often overlooked design measures for things like wiring harnesses and connectors.
The physical connections.
Absolutely critical for robust electrical connections in a harsh automotive environment. You can have the best chip in the world, but if the connector fails...
Game over. Wow, that's incredibly granular. It sounds like every single potential failure, no matter how small, has to be considered and accounted for. It makes you wonder, what's the most common misconception people have about faults in a car, even those of us who think we're pretty tech-savvy? Is it really those latent faults? Are they the ones you truly never see coming?
Absolutely. I think latent faults are often the most misunderstood danger. Most people think a fault means something immediately breaks, a warning light comes on, the car stops working properly.
It's something obvious.
Right. But the truly insidious ones are those sleeping faults. They don't cause any immediate effect. They only become critical when a second, completely unrelated issue pops up.
Like a perfect storm scenario.
Exactly. They're like a ticking time bomb waiting for just the right or wrong conditions to detonate. That's precisely why the standard is so obsessive about uncovering them, classifying them, and ensuring they're detected or they're risk managed before they can combine with another fault to cause a hazardous event.
So how do the automotive safety integrity levels, the ASILs, play into these requirements? We've talked about ASILs before, but what's their specific connection here at the hardware level?
The ASILs are absolutely central. They drive everything. Think of ASILs as the ultimate safety grading system applied to specific safety goals related to potential hazards.
A, B, C, D.
Right. For ASIL, B, C, and D safety goals, those higher, more critical levels, the target values for things like hardware architectural metrics, and the probabilistic evaluation of random hardware failures, which we'll definitely delve into later. Those targets must be thoroughly considered when defining the specific values and parameters for individual hardware elements. The higher the ASIL, the more stringent these requirements become. It drives greater rigor in design, implementation, and importantly, verification.
So an ASIL D component needs way more attention than an ASIL B.
Way more. For example, a simple interior light might be QM, quality managed, or maybe ASIL A. But a critical braking system component could easily be ASIL D, meaning it requires an almost obsessive level of attention to detail and fault mitigation strategies.
And the hardware-software interface, the HSI, you mentioned that earlier, is it defined once at the system level and then just handed over? Or is there more refinement during hardware development? It seems like such a critical handoff point.
Oh, it's definitely not set in stone. It undergoes critical refinement during hardware development. The HSI specification, which gets its initial definition at the system level, is meticulously detailed and refined in this phase, Part 5.
Why the refinement?
It's essential to ensure the correct control and usage of the hardware by the software. This refinement precisely outlines every single safety-related dependency between the hardware components and the software components that interact with them.
And who's responsible for that?
It's very much a joint responsibility. This isn't just a hardware team's job or just a software team's job. Both the hardware and software development teams must work closely together to verify the adequacy and correctness of this refined HSI. They have to guarantee that their respective parts will integrate seamlessly and safely.
Because any miscommunication there
could open up serious safety loopholes. You need absolute clarity on how software controls hardware features, reads status registers, handles interrupts, everything.
So once all these incredibly detailed requirements are defined and the HSIs refined,
Yeah.
how do you actually know they're correct and effective? What's the verification process like just for these hardware safety requirements themselves?
Right. Before you even start designing in detail, these hardware safety requirements aren't just defined and thrown over the wall, they're rigorously verified. This verification process ensures their consistency, first with the technical safety concept and the overall system design.
Checking back upwards.
Exactly. It confirms their completeness against all higher-level technical safety requirements, making sure nothing was missed in that flow down. It checks their consistency with any relevant software safety requirements via that HSI. Ultimately, it's about ensuring their overall correctness and accuracy. You leave no stone unturned before you commit to designing the hardware based on them.
So we've laid out the detailed safety requirements, the what needs to be safe. But the real magic, I guess, where the abstract truly becomes tangible is in the design itself. This isn't just about drawing circuit boards, is it? What are the overarching objectives when engineers actually start building out this hardware design?
You're absolutely right. It's far, far more than just laying out circuit boards. The core objectives are multifaceted. First and foremost, it's about creating a hardware design that actively supports safety-oriented analyses, like the FMEAs we'll talk about, and readily incorporates the results from those analyses.
Okay.
This design must, of course, fulfill all the specified hardware safety requirements we just discussed and the refined HSI specifications. It also has to be perfectly consistent with the overall system architectural design. And it needs to exhibit all the required hardware design properties, things like robustness, simplicity, and clear interfaces.
But it's not just about safety right now in the design phase, is it? It's also about what happens after the car leaves the factory. The entire life cycle seems important here.
Exactly right. A crucial forward-looking aspect of this phase is specifying requirements for functional safety throughout the entire product life cycle.
The whole life.
The whole life. That means considering safety implications during production, throughout the vehicle's operation, potentially for decades during service and maintenance, and even at the end of its life, during decommissioning. How do you safely take this thing apart?
Wow.
And finally, there's the verification aspect tied to the design itself. Confirming that the hardware design can meet all safety requirements, validating any assumptions made for integrated safety elements out of context, or COOCs.
COCs.
Yeah, COOCs essentially pre-designed, often pre-certified components like a specific microcontroller or sensor that you buy in. You need to make sure your assumptions about how it works are valid in your specific system, and ensuring the suitability of safety-related special characteristics identified during design.
Okay, let's talk about the hardware architectural design first. That's the big picture, the blueprint of the physical system, right? How are those meticulous safety requirements actually incorporated into this overall hardware architecture?
This is exactly where those specified hardware safety requirements are translated into the structural design of the hardware. It involves meticulously allocating these requirements to individual hardware elements, often right down to a specific chip, a power supply, or even a distinct circuit block within a chip.
Assigning responsibility.
Precisely. And crucially, each hardware element then inherits the highest ASIL of any requirement assigned to it.
The highest ASIL wins.
Yes, this cascading effect is critical. It ensures that even a component with perhaps a seemingly low inherent risk is treated with the rigor appropriate for the most critical safety function it supports. For instance, if a simple power supply provides voltage to both an ASIL B system, maybe infotainment related, and an ASIL D system like braking control,
Right.
that power supply absolutely must be designed, analyzed, and verified as ASIL D. No cutting corners.
And what principles guide this architectural design to prevent systematic faults? These aren't the random failures like a component just wearing out, right? These are errors built into the design itself.
That's exactly right. Systematic faults are flaws in the specification, design, or manufacturing process. To avoid these, the hardware architectural design must exhibit specific properties as outlined in the standard. Table 1 gives good examples.
Okay.
These include things like modularity. This enables the reuse of proven design blocks, like maybe temperature detection circuits or error-correcting code, ECC blocks, without modification. This is vital for efficiency, consistency, and reducing the chance of introducing new errors each time.
Makes sense. Reuse what works.
Exactly. Then there's adequate granularity. This means the architectural representation, the diagrams and descriptions, must provide sufficient detail to clearly demonstrate the effectiveness of the safety mechanisms. You need to be able to see the specifics to confirm it actually works as intended.
Not too high level.
Not too high level, not too low level, just right. And finally, simplicity is key, actively avoiding unnecessary complexity in interfaces and components. Complexity is often where systematic faults hide.
Keep it simple.
Keep it simple, stupid. The KISS principle applies strongly here. Other methods listed in the Standards Table 1 include using hierarchical design, having precisely defined interfaces between blocks, designing for maintainability for service later on, and ensuring comprehensive testability throughout development, production, service, and operation. These are essentially engineering best practices, but viewed through a very sharp safety-critical lens.
It sounds like they're building in safeguards against human error and design flaws right from the absolute start. What about environmental and operational influences? Things like extreme temperatures, vibrations, or electromagnetic interference EMI, which can cause all sorts of unexpected issues in the real world.
Non-functional causes for failure, those environmental and operational stresses, are absolutely critical and must be considered during the hardware architectural design. This includes influences such as extreme temperatures, hot and cold prolonged vibrations from the road or engine, the potential presence of water or dust ingress, electromagnetic interference from other systems or external sources, general electrical noise factors, or even signal crosstalk originating from adjacent hardware components or the vehicle's complex electrical environment.
So the design has to anticipate that.
It must inherently account for these real-world conditions. This means components are chosen and the physical layout is designed in a way that tolerates or actively mitigates these external stresses. The goal is to prevent them from leading to functional failures or safety goal violations.
So once the big picture architectural design is set, then you drill down into the hardware detail design. What are the considerations at this finer level of granularity? Now we're talking individual components.
Yes, now we're getting down to the specifics of circuits and component selection. At the detailed design level, engineers are expected to apply lessons learned from past projects to actively avoid common design faults. You don't want to repeat old mistakes.
Learn from experience.
Absolutely. They continue to consider those non-functional causes for failure, like temperature extremes or EMI, but now at the level of individual hardware parts and how they interact. The mission profile, how the part is expected to be used over its lifetime, and the specific operating conditions of each hardware part or component must also be carefully considered. This ensures it operates reliably within its specified parameters under real-world usage scenarios.
So making sure it can handle the job it's given.
Right. You don't want failures just because of the actual intended use. Finally, robust design principles are emphasized. This is often exemplified by conservative component specification, maybe choosing a resistor with a higher power rating than strictly calculated, or a capacitor with a higher voltage rating to withstand stress factors. It provides a larger buffer against the unexpected and ensures longevity.
Now, here's where it gets really interesting for me. Safety analyses during design. This is where you proactively hunt for potential problems, right? What's the purpose of these analyses, and what methods are typically used to catch those potential flaws early, before anything is even built?
You got it. These analyses serve a crucial dual purpose. Initially, early in the design phase, they support the hardware design specification by identifying potential failure modes and weaknesses. Finding issues on paper is much cheaper than finding them in silicon.
Definitely.
Then subsequently, after the design is more mature, these same analysis techniques are used for rigorous verification of the completed design. The key methods, as recommended by the standard in Table 2, are inductive analysis, which is highly recommended,
Inductive.
and deductive analysis, which is also recommended. They offer different perspectives.
Can you give us a concrete example of each, maybe, and how they help catch issues?
Certainly. For inductive analysis, the absolute core tool is failure mode and effects analysis with diagnostic analysis, usually shortened to FMEDA.
FMEDA. Heard of that one?
It's a powerful bottom-up approach. You systematically identify individual hardware component failure modes, for example, a specific resistor failing open or a transistor failing short-circuited. Then, for each identified failure mode, you meticulously evaluate its potential effects on the overall item's behavior, especially regarding safety goals. And crucially, you assess the diagnostic coverage provided by any safety mechanisms designed to detect or mitigate that specific failure mode.
So asking, what if this breaks?
Exactly. It's about asking, if this specific part fails in this particular way, what happens to the safety of the system? And importantly, can our safety mechanisms detect it or control it? This helps you pinpoint weak spots in the design and engineer an effective countermeasures or diagnostics.
Okay, that's bottom up. What about deductive?
For deductive analysis, fault tree analysis, or FTA, is very commonly used. This is a top-down approach. You start with a specific hazardous event, a top event in FTA terms, like unintended acceleration or loss of braking.
The bad outcome.
The bad outcome, exactly. And then you work backwards systematically to identify the combination of lower-level component failures or external events, or even software errors that could logically lead to that top hazardous event. FEMEA results can actually feed into an FTA, providing the basic failure events, the root causes, at the very bottom of the fault tree branches.
So they work together.
They are very complementary, yes. Using both gives you a much more comprehensive view of potential failure paths and system vulnerabilities.
Okay, so you're analyzing what could go wrong, but then you have to classify these faults. This is where it gets truly fascinating, I think. How does the standard classify different types of faults, and why is that classification so incredibly important?
This classification is absolutely critical. It's fundamental for understanding the true risk profile of the system and for directing mitigation efforts effectively. You need to know what kind of beast you're dealing with. The analysis aims to classify faults into distinct categories, as detailed nicely in Annex B and C of the standard.
Okay, what are the categories?
First, we have safe faults. These are failures that, even if they occur, do not significantly increase the probability of a safety goal violation. They might cause a minor nuisance, maybe a non-safety related light blinks incorrectly, but they won't lead to a dangerous situation. They don't contribute negatively to the safety metrics.
Right, the harmless ones.
Relatively harmless, yes. Then, at the other extreme, you have single-point faults. As the name suggests, a single failure of a hardware part directly leads to a violation of a safety goal, assuming no safety mechanism is in place or effective. Imagine a single critical sensor failing in a way that directly causes your brakes to lock up unexpectedly. These are incredibly dangerous.
The ones you really need to prevent.
Absolutely. They require stringent mitigation, often through redundancy or highly effective safety mechanisms with high diagnostic coverage. Close behind are residual faults. These are failures that would be single-point faults, meaning they could directly violate a safety goal on their own, but they are not fully covered by the implemented safety mechanisms. There's a remaining unmitigated risk associated with them that needs to be quantified and managed.
So the safety mechanism didn't quite catch it all.
Or maybe it catches it but can't react fast enough. There's some residual risk left over. And finally, we have multiple point faults. These are failures that only violate a safety goal if multiple independent faults occur. For example, if fault A happens and then completely separately fault B happens, and only the combination of A and B occurring leads to a hazard.
Okay, needs more than one thing to go wrong.
Right. But these are further subclassified because how they manifest is crucial for understanding their hidden dangers.
So what are the crucial subclassifications for these multiple point faults? This sounds important.
They are crucial for assessing those hidden risks. The main subclassifications are latent faults. These are multiple point faults that are not detected by any safety mechanism, nor are they perceived by the driver within a specific time frame called the multiple point fault detection interval. They remain hidden, dormant, silently waiting until that second independent fault occurs, completing a hazardous chain of events. These are often the most challenging to manage because, by definition, you don't even know they're there until potentially too late.
The really sneaky ones.
Exactly. Detected multiple point faults. These are multiple point faults that are detected by a safety mechanism. So while they still require multiple failures to cause a hazard, the detection mechanism ensures the system can take action when the first fault occurs, perhaps warning the driver, or transitioning to a degraded but safe mode, potentially preventing the second fault from ever leading to the hazard.
So detection is key.
Detection is absolutely key. Perceived multiple point faults. These are faults that, even if they're part of a multiple point failure sequence, are perceived by the driver. This perception might be through abnormal vehicle behavior, a strange noise, or some other cue. This perception allows the driver to take appropriate action, like pulling over safely, and thus prevents the ultimate safety goal violation.
So a lot of this really hinges on the effectiveness of these safety mechanisms, doesn't it? How do you actually prove that they are working as intended? And crucially, how quickly do they need to act? Time seems critical here.
Time is absolutely critical. Evidence of diagnostic coverage, or DC, is essential for both residual faults and latent faults. DC, remember, refers to the ability of safety mechanisms to detect these faults, usually expressed as a percentage.
Right.
And beyond just detection, safety mechanisms must achieve and maintain a safe state within specific critical time intervals. Two key ones are the fault-tolerant time interval, or FTTI,
FTTI.
and the maximum fault handling time interval, or MFHTI.
MFHTI. Okay, what's the difference?
Think of it this way. The FTTI is the absolute maximum time the system has from the occurrence of a fault until a potential hazard occurs if nothing is done. It's dictated by the physics of the situation how quickly things can go wrong. Maybe it's milliseconds for a steering failure or longer for something else.
The window of opportunity.
Exactly. The MFHTI, on the other hand, is the maximum time the safety system is allowed to take to detect the fault, react, and transition the system to a defined safe state. The MFHTI must always be shorter than the FTTI.
Got to react faster than the hazard develops.
Precisely. If a safety mechanism cannot detect the fault and bring the system to a safe state within these critical timings, it cannot be considered effective for things like acyl decomposition or for taking credit in the quantitative metrics we'll discuss later. There's also the multiple point fault detection interval, which specifically specifies the maximum time within which those dangerous latent faults must be detected. This is paramount for preventing those hidden issues from accumulating silently.
What's fascinating here is that the standard provides quite a bit of guidance on evaluating diagnostic coverage, right? I remember seeing tables related to different mechanisms.
Yes. Annex D of the standard is incredibly valuable here. It provides detailed guidelines and examples for estimating diagnostic coverage, DC. It categorizes typical DC levels as low, medium, and high, often corresponding to roughly 60%, 90%, and 99% coverage, respectively.
What?
And then it applies these to various hardware elements like microcontrollers, memory, communication buses, sensors, and their common failure modes. Crucially, it links these DC levels to different types of safety mechanisms.
Can you give some examples?
Sure. For processing units, Annex D lists techniques like software-based self-tests, checking instruction execution, registers, using software to diversify redundancy, or hardware redundancy like dual-core lockstep, where two processors run the exact same task and constantly compare results. Any mismatch indicates a fault.
Like having a backup brain checking the main one.
Kind of, yes. For communication buses, it details methods like adding parity bits, one-bit hardware redundancy, or more robust methods like using cyclic redundancy checks, CRCs, message sequence counters, or timeout monitoring to detect lost or corrupted messages, information redundancy. For sensors, it lists things like simple valid range checks on the output, or more complex sensor correlation where you compare readings from multiple diverse sensors measuring the same physical quantity. This detailed guidance really helps engineers select appropriate safety mechanisms and then justify the level of diagnostic coverage they achieve.
And this all feeds back into the mathematical classification of failures, doesn't it? That total failure rate, lambda, and its breakdown.
That's right. The standard, particularly in Annex C, explains the fundamental equation where the total failure rate of a component, symbolized by lambda, is broken down into its constituent parts. LSPF for single-point faults, LRF for residual faults, OMPF for multiple-point faults, which itself includes latent and detected, and RS for safe faults.
So LSPF plus LRF plus LMPF plus LRS.
Exactly. Then, the diagnostic coverage, DC estimates we just discussed, are directly used to mathematically estimate the failure rates associated with residual faults, RRF, and latent faults, OMPF, latent. This provides the quantitative basis for the hardware architectural metrics we'll delve into next. It literally puts numbers on how many potentially dangerous hidden or uncovered faults you might expect from a component.
Now, this raises a really important practical question. What happens when a safety mechanism controls a fault, meaning it prevents the bad outcome, but doesn't actually detect it or signal it? Seems like a really tricky scenario, almost like sweeping a problem under the rug without knowing it's there.
This is a critical nuance, especially for correctly calculating the latent fault metrics, and it's a point the standard clarifies very well, often using examples like those in Annex H. Imagine a simple electronic filter circuit. Its job is to remove electrical noise from a sensor signal, acting as a safety mechanism to prevent that noise from affecting a critical downstream function.
Okay, makes sense.
Now, if this filter works perfectly and removes the noise, the downstream function sees a clean signal and operates correctly. The filter has controlled the fault, the noise. However, if the filter provides no detection or indication that the noise was ever present on the input signal, then the original fault it's controlling the noise itself can be considered latent.
Because nobody knows it happened.
Exactly. It's hidden because the filter makes the system appear to be working correctly, even though an underlying fault condition, the noise source, exists. The danger is if the filter itself were to fail later, that noise could suddenly get through, potentially causing a hazard, and you had no prior warning.
Ah, I see.
This is in stark contrast to a safety mechanism that performs both detection and control. In that scenario, once a fault is detected, it typically leads to a defined safe state, or at least a driver notification, like a warning light. Because the fault is actively managed and made visible, that fault is not considered latent, even if it's part of a multiple-point sequence. This distinction really highlights why achieving high diagnostic coverage detection is so important. It's not just about preventing the immediate hazard, but about ensuring faults don't accumulate invisibly, creating a hidden, ticking vulnerability.
So it's really about making sure you're not just patching symptoms, but truly understanding and making visible any underlying issues that could cause trouble later. Okay, one more analysis type mentioned. Dependent failure analysis, DFA. That sounds like it's about ensuring independence, right? Preventing one thing from taking down multiple others.
Exactly. DFA is all about ensuring that elements or safety mechanisms intended to be independent for safety reasons, like redundant sensors or processors, truly are independent in practice. It looks for potential common cause failures.
Common cause failures.
Yeah, a common cause failure is a single event or root cause, like maybe a power supply glitch, a flaw in a shared software library, overheating, or even a single physical impact that could defeat multiple supposedly independent safety mechanisms or functions simultaneously. DFA systematically identifies potential sources of dependency, like shared power rails, shared clocks, physical proximity, common algorithms, and ensures adequate measures are taken to mitigate them. This prevents a single initiating event from undermining the entire safety architecture, especially where redundancy is used to meet high ASIL requirements.
All right, so we've talked about designing safety in, analyzing potential failures. Now we need to talk about measuring it quantitatively. This takes us to the evaluation of random hardware failures, essentially, putting hard numbers on safety. What's the objective here, and why is this quantitative approach so critical in ISO 26262?
The overarching objective of this phase, covered in clauses 8 and 9, is to provide compelling quantitative evidence that the residual risk of a safety goal violation, specifically due to random hardware failures, those unpredictable failures that happen over time, is sufficiently low.
Sufficiently low. What does that mean in practice?
What sufficiently low means in this context isn't absolute zero risk, which is impossible. Instead, it means the calculated risk is comparable to or lower than the risks associated with similar systems or functions already in use on the road and widely accepted by society as being safe. It's about setting a quantifiable benchmark, often based on existing safe systems, rather than aiming for some unobtainable theoretical perfection.
Okay, comparing against known safe systems. And how do you do this?
The standard offers two alternative but related methods for this quantitative evaluation. First, there are the hardware architectural metrics, covered in Clause 8. Second, there's the probabilistic metric for random hardware failures, or PMHF, along with an alternative called the evaluation of each cause, or EEC, both detailed in Clause 9.
Let's start with those hardware architectural metrics in Clause 8 then. What's their specific purpose, and what exactly do they tell you about the safety of the hardware design?
Their main purpose is to quantitatively evaluate the effectiveness of the item's architecture itself in coping with random hardware failures, specifically focusing on how well it handles single-point and latent faults. These metrics are seen as complementary to the overall probabilistic assessment done via PMHF or EEC.
So they focus on the structure.
Exactly. Their scope is applied at the item level, but they focus specifically on the safety-related electrical and electronic hardware parts that could significantly contribute to a safety goal violation if they fail, especially through single-point faults, residual faults, and latent faults. Interestingly, even for electromechanical parts like relays or motors, only their electrical failure modes and rates are typically considered for these specific architectural metrics. They essentially give you a score on how well your chosen design structure prevents or catches these particularly dangerous types of faults.
How do you even begin to estimate failure rates for all these tiny hardware parts? Is there a standard way to get that lambda value, the rate at which components are expected to fail randomly?
Estimating failure rates, lambda, for hardware parts is absolutely crucial for these calculations, and it's not trivial. The standard outlines a few accepted ways as per clause 8.4.3.
Okay.
One very common method is to use data from recognized industry or military reliability handbooks and standards, like SN 29500, IEC 61709, or the older ML HDBK 217. These databases compile vast amounts of empirical data on component reliability across different operating conditions and generally provide conservative, well-accepted failure rate values.
So using established data.
Right. Another approach, if you have enough data, is to use statistics based on actual field returns from similar products already in use. Provided the estimated failure rate derived from this data has a comparable confidence level, the standard suggests at least 70%. This means you need enough real-world data to be statistically confident in your numbers.
Using your own history.
If it's relevant and robust, yes. And finally, particularly for novel designs, custom ASICs, or when empirical data is scarce, expert judgment can be used. However, this must be founded on a structured engineering approach with clear quantitative and qualitative arguments justifying the estimated rates. It can't just be a guess.
Rigorous justification needed.
Absolutely. Once these base failure rates are estimated for each component, the total failure rate for a safety-related hardware element can be broken down, as we discussed, into its components using the results of the FMEDA. SPF for single-point faults, LRF for residual faults, LMPF for multiple-point faults, latent and detected, and OAS for safe faults. This detailed breakdown is fundamental for calculating the architectural metrics.
Okay, so once you have those failure rates broken down, you can start calculating the actual metrics. Tell us about the first one, the single-point fault metric, or SPFM. What does that measure and why is it important?
The single-point fault metric, or SPFM, directly quantifies the robustness of the item's architecture against those most dangerous faults: single-point faults and residual faults. A high SPFM indicates that the proportion of the total failure rate attributed to these direct paths to failure is acceptably low.
So a high score is good.
A high score is very good. It's essentially a ratio showing how much of your total safety-related failure rate is not due to single-point or residual faults. The calculation, shown in Annex C, effectively sums the failure rates of all safe faults and detected perceived multiple-point faults and divides by the total failure rate excluding safe faults.
And what are the targets?
The standard gives specific target values based on SL. For an ASIL-B system, the target SPFM is typically on 90%. For ASIL-C, it jumps to even 97%. And for the highest level ASIL-D, it's even 99%. These are extremely high percentages, reflecting the absolute imperative to minimize these direct paths to danger through architectural means like redundancy or strong safety mechanisms.
Can you give an example?
Sure. Annex E of the standard provides worked examples. One might show, say, an ASIL-C system calculation resulting in an SPFM of 96.5%. In that case, it falls just short of its 97% target, which would require the engineers to either refine the design further to eliminate more single-point residual faults, improve diagnostic coverage, or provide a very strong justification for why 96.5% is still acceptable in that specific context.
And then there's the second metric, the latent fault metric, or LFM. How does that differ from the SPFM, and why is it so important given our earlier discussion about those sneaky latent faults?
The latent fault metric, or LFM, specifically reflects the item's architectural robustness against those hidden, latent, multiple-point faults. Remember, these are the faults that aren't detected and could combine with a second fault later. This robustness is achieved either through diagnostic coverage, the system finding the first fault of the pair, or sometimes by the driver's perception of that first fault before the second one occurs and leads to a safety goal violation.
So it measures how well you find the hidden stuff.
Exactly. A high LFM means a low proportion of the multiple point faults are latent. Most are either detected or perceived. Its calculation, also in Annex C, focuses on the ratio of latent fault failure rates compared to other fault types.
And the targets here, lower than SPFM.
Yes, the targets are still demanding but generally lower than for SPFM, reflecting the fact that multiple faults need to occur. The typical target values are ASIL-B 60%, ASIL-C 80%, and ASIL-D 90%. This metric is crucial because if you don't detect or perceive latent faults effectively, they can accumulate silently, and when that second fault eventually strikes, it could bypass your safety mechanisms completely because the first fault had already disabled part of the safety system without anyone knowing.
That makes sense. Do the examples show meeting these targets?
Often, yes. An example system in Annex E might calculate an LFM of, say, 91.6% for ASIL-C, which comfortably exceeds the 80% target, indicating the design is quite effective at uncovering or managing these potentially hidden issues.
So those two metrics, SPFM and LFM, give you a good handle on the hardware architecture's inherent ability to deal with individual faults. But then you have the overall probabilistic evaluation of the PMHF and EEC in Clause 9. Which method do you choose, and what's the big difference between them?
Right. For ASIL B, C, and D safety goals, the standard mandates that the item must comply with the requirements of either the PMHF method or the EEC method. You generally choose one approach for evaluating the overall probability of failure.
One or the other?
One or the other. The main difference is scale and perspective. PMHF aims for a single overall probability value for the violation of a safety goal for the entire item. EEC, on the other hand, looks at each potential cause of failure, each single point, residual, and plausible dual point failure individually.
Let's delve into PMHF first, the probabilistic metric for random hardware failures. What's its main objective, and what about those incredibly tiny target numbers we often hear associated with it? Yeah, 10 to the minus something.
The PMHF's objective is to provide a quantitative estimate of the average probability per hour of a violation of a specific safety goal due to random hardware failures, calculated over the item's entire operational lifetime, e.g., 15 years, 200,000 kilometers.
Average probability per hour.
Exactly. And yes, the target values associated with PMHF are indeed incredibly small. For ASIL-D, the generally accepted target is less than 10 to 8 failures per hour.
That's one failure in 100 million hours of operation.
It sounds impossibly small, doesn't it? For ASIL-C and ASIL-B, the target is typically less than 10 to 7 failures per hour, 1 in 10 million hours. It's really important to understand that these values are often conservative benchmarks, primarily used for comparing the predicted reliability of new designs against established norms, rather than representing an absolute guaranteed real-world failure probability for any single vehicle off the production line.
They're relative targets for design assessment.
Primarily, yes, although demonstrating compliance is a mandatory part of the safety case.
What are the key considerations when you're actually calculating this PMHF value? It sounds incredibly complex, trying to bring together so many different factors.
It is indeed complex. The calculation crucially considers the item's specific architecture, the estimated base failure rates for all the relevant hardware parts, the failure modes identified in the FMETA, single point, residual, multiple point, and of course the diagnostic coverage, DC, achieved by the various safety mechanisms for each failure mode.
Okay, all the stuff we've discussed.
Right, but what's absolutely crucial and sometimes tricky to determine accurately is the exposure duration. This is the time interval during which a fault remains undetected or uncontained, and could, if a second fault occurs or the operating conditions demand it, lead to a safety goal violation.
How long the danger window is open.
Exactly, and this duration varies wildly depending on the type of fault, the monitoring strategy, and the required reaction. For example, if a fault is detected by continuous hardware monitoring that triggers an immediate safe state transition, like shutting down power, the exposure duration might be mere milliseconds. But for an unmonitored latent fault, that exposure duration could effectively be the vehicle's entire operational lifetime, potentially years. This obviously leads to a much higher contribution to the overall probability of violation over time. The standard also provides guidance and examples for scenarios where the driver is alerted or requested to stop or bring the vehicle to a workshop for repair, often using typical trip durations or repair intervals, like 1 hour for a passenger car trip, as the exposure time for certain fault types.
What happens if you do the math and you don't meet these incredibly tough PMHF targets? Is it just game over for the component or the system design?
Not necessarily game over, but it certainly requires significant attention. If a calculated PMHF value exceeds the target for the required ASIL, a rationale can often be provided within the safety case to justify how the safety goal is still achieved despite the numerical result.
How can you justify missing the target?
Well, the rationale might involve identifying the top contributing failure modes to the high PMHF value and demonstrating that further design improvements have been made to address them specifically. It could also involve rigorously reviewing and potentially refining the underlying base failure rate estimates if conservative values were initially used. Conducting deeper reliability investigations or leveraging extensive positive field experience from highly similar components already in mass production can also be part of the justification. Sometimes, implementing additional verification measures during production or service, or demonstrating that the design truly represents the achievable state-of-the-art for that technology can be accepted. It's about building a comprehensive safety argument, proving the residual risk is still acceptably low, even if the initial calculation didn't hit the somewhat arbitrary target value.
So it's about the overall safety argument, not just one number in isolation.
Precisely, though meeting the target is obviously the preferred path.
And what about the alternative method mentioned in Clause 9, the evaluation of each cause, or EEC? How does that approach differ from the global PMHF calculation?
The EEC offers a distinct alternative approach. Instead of calculating that single overall average probability metric, PMHF, it performs an individual evaluation of each significant potential cause of a safety goal violation. This means looking individually at each identified single-point fault, each residual fault, and each plottable dual-point failure scenario at the hardware part level.
Wow, that sounds even more detailed.
It can be, in a way. It involves following qualitative evaluation procedures, which are nicely illustrated by flowcharts in figures 3 and 4 of the standard. Essentially, for each potential cause of failure, you check if it's acceptable based on its failure rate class ranking and the effectiveness of the diagnostic coverage provided by any relevant safety mechanism. It's a more granular, qualitative, case-by-case assessment rather than a single quantitative sum.
Failure rate class ranking, what does that mean? Is that like a difficulty score for how likely something is to fail?
That's a pretty good analogy, actually. Think of failure rate class ranking, like assigning a grade or a category, say, class 1, class 2, class 3, and so on, based on how often a hardware part is expected to fail randomly, purely based on its intrinsic reliability and operating conditions before you consider any safety mechanism.
Okay, like a baseline failure tendency.
Exactly. The standard defines these classes. Example, class 1 for very low failure rates, class 3 for higher rates. This concept is similar to the occurrence levels often used in a traditional FMEA, where maybe a 1 is assigned to failure modes with the lowest expected occurrence rate. This classification, based on the part's base failure rate, provides a clear reference point. The EEC method then uses this class ranking, combined with the diagnostic coverage, to determine if the risk associated with that specific fault cause is acceptable according to predefined tables 7, 8, and 9 in the standard, for the relevant ACL. It gives you a structured way to judge the risk of each individual failure path.
So we've designed safety into the hardware, we've analyzed it, we've measured its safety using these quantitative metrics. Now we need to prove it all actually works when it's put together in the real world. That brings us to hardware integration and verification, covered in Clause 10. What's the core objective of this final crucial stage?
The core objective of this clause, hardware integration and verification, is quite simply to ensure that the developed hardware item, once assembled, fully complies with all of its specified hardware safety requirements. It's really the moment of truth where all the careful planning, the detailed design work, and the complex safety analyses are put to the ultimate test in a real-world integrated hardware environment.
And what do these integration activities actually entail? Are we talking about literally bringing the physical components together, soldering them onto boards and making them talk to each other?
Absolutely. It starts with the hands-on process of physically bringing together the individual hardware elements, the chips, the resistors, the connectors, assembling them onto the printed circuit boards, and making sure they are connected correctly and communicate as intended according to the design and the HSI.
Building the actual thing.
Building the actual thing. This stage also requires close coordination with the broader system-level integration and test strategy, which would have been defined earlier in the V model. You need to know how the hardware testing fits into the overall vehicle testing plan. A critical aspect here, mentioned in 10.4.3, is hardware qualification.
Qualification, what does that involve?
It means that safety-related hardware parts, especially key components like microcontrollers or power devices, must be qualified using well-established procedures, often based on widely accepted worldwide quality standards. For instance, this could involve extensive environmental testing according to standards like ISO26262-Part, which details how to test electronic components under various environmental stresses found in a vehicle, extreme temperatures, humidity, salt spray, vibration, shock, and so on.
Putting them through the ringer.
Exactly. Or it might involve specific electronic part qualification using standards like AEC-Q 100 for integrated circuits or AEC-Q 200 for passive components, which are standards developed by the Automotive Electronics Council. This qualification process happens often before integration and ensures the inherent quality, reliability, and robustness of the components themselves. It's about making sure you're building with the best possible, most reliable ingredients from the start.
And then comes the rigorous testing of the integrated hardware. How are these test cases even derived? It must be an enormous undertaking to think of every possible scenario and interaction.
It is indeed a significant undertaking, and it needs to be systematic. As Table 10 in the standard indicates, test cases are derived through a combination of meticulous methods. This includes detailed analysis of the hardware safety requirements themselves and the internal and external interfaces, understanding every input signal, output signal, and control mechanism.
Checking against the requirements.
Yes, directly tracing tests back to requirements. It also involves generating and analyzing equivalence classes, grouping similar inputs, and boundary values. Testing at the very edges and just beyond the edges of acceptable operational parameters, not just testing typical operating points.
The testing the limits.
Precisely. Sometimes it even involves error guessing, which, despite the slightly informal name, is actually a highly skilled process. It relies on engineers using their past experience, knowledge of common failure modes in similar technologies, or expert judgment to predict where faults or unexpected behaviors might occur and designing specific tests to provoke them. They also consider analysis of functional dependencies between components, common limit conditions like low battery voltage, and various environmental and operational use cases derived from the vehicle's mission profile. It's a very comprehensive approach aimed at ensuring every possible scenario, from normal operation to the most extreme conditions, is adequately tested.
And what about the actual verification of the implementation once it's built? What kind of tests confirm that the hardware safety requirements are actually met in the physical hardware and that the safety mechanisms perform their job correctly?
The standard, in Table 11, outlines the key types of tests specifically for verifying the hardware implementation against its safety requirements. There's functional testing, which is fundamental. It simply verifies that the hardware exhibits its specified characteristics and functions correctly under normal operating conditions, basically. Does it do what it's supposed to do according to the spec?
The basic check.
The basic check, yes. Then, crucially, fault injection testing is often performed, especially for semiconductor components like microcontrollers or ASICs. This is where faults like short circuits, open circuits, stuck-at signals, or corrupted data are deliberately introduced into the hardware while it's operating.
Intentionally breaking things.
Intentionally introducing specific fault conditions? Yes. The goal is to observe whether the implemented safety mechanisms detect the fault and react as intended, for example, by signaling an error, switching to a redundant component, or transitioning the system to a defined safe state, all within the required time limits, like the MFHTI. It's like intentionally throwing a precisely aimed wrench into the system to see if the safety net catches it properly.
That sounds intense.
It can be. And finally, there's electrical testing. This verifies compliance with specified electrical parameters, like operating within defined voltage ranges, handling expected current loads, maintaining signal integrity, and ensuring immunity to electrical disturbances. It confirms basic electrical robustness.
It sounds like they're intentionally breaking things to make sure the system can handle it. I imagine the test labs sometimes look like a mad scientist's playground, pushing components to their absolute limits.
You're not entirely wrong. Sometimes it feels that way. We often joke that a big part of our job is to find every conceivable way to make a system fail in the lab, so it hopefully never surprises us with a new failure mode out on the road. There's definitely a certain satisfaction in putting a component through an absolute torture test and seeing it emerge still functioning correctly, or at least failing safely as designed.
I bet. What other kinds of stress tests are involved?
Beyond those core verification tests, there's typically an extensive set of tests aimed specifically at verifying durability, robustness, and operation under various real-world stresses, often detailed in Table 12. This includes comprehensive environmental testing, assessing hardware performance under cycles of extreme temperature, varying humidity, and prolonged vibration profiles, often following standards like the ISO26262-Part series we mentioned earlier.
Simulating the car environment.
Exactly. There's also expanded functional testing, which involves pushing the hardware with rare, unexpected, or extreme input conditions that might occur infrequently in the real world but could cause problems. Statistical and worst-case testing might use statistical distributions derived from real-world vehicle usage data, mission profiles, to create test scenarios and specifically test components at the marginal worst-case combinations of environmental conditions. For example, maximum temperature combined with minimum voltage.
Finding the weakest points.
Trying to, yes. Over-limit testing deliberately pushes elements beyond their specified operational limits to understand their failure modes and determine their actual robustness margins. How much abuse can they really take before failing? Mechanical testing, especially for enclosures, connectors, or assemblies, assesses physical properties like tensile strength, resistance to shock, or fatigue life under repeated stress, often following standards like ISO26262-Part.
Physical durability.
Right. Accelerated life testing attempts to predict long-term reliability and wear-out behavior under normal conditions by subjecting the hardware to significantly higher stresses, like higher temperature or voltage, for a shorter period. And critically important in modern vehicles is EMC and ESD testing. This ensures electromagnetic compatibility, that the hardware doesn't emit excessive interference and isn't susceptible to interference from other systems or external sources, and also confirms resistance to electrostatic discharge events, following specific automotive standards like ISO 7637 for electrical disturbances, ISO 11452 for radiated immunity, or ISO 10605 for ESD.
So it doesn't get scrambled by radio waves or static electricity.
Precisely. There's even chemical testing mentioned, assessing resistance to various chemical loads the hardware might encounter, like road salt, cleaning fluids, or fuel vapors, often based on ISO 16750-5. It's an incredibly exhaustive battery of tests designed to build confidence that the hardware will be resilient and safe in virtually every conceivable operating scenario throughout its intended life.
So when we tie all of this together, this entire process, from the initial concepts and the incredibly stringent requirements, through the detailed design and analysis, the grueling tests, and the complex quantitative evaluations, what's the unifying thread that holds this entire hardware development process for functional safety together? What's the biggest takeaway for our listeners from Part 5?
I think the ASILs, the automotive safety integrity levels, are the absolute unifying thread running through everything we've discussed in Part 5. They are not just arbitrary classifications assigned at the beginning. They are the fundamental drivers of the entire hardware development process.
They dictate the level of effort.
They dictate the required rigor, the specific methods to be applied, and the acceptance criteria at every single step. From the level of detail needed in the specifications, to the types of safety mechanisms required, the depth of analysis like FMETA, the target values for the quantitative metrics like SPFM, LFM, and PMHF, and the extent of testing and verification needed. It's the ASL assigned to the safety goal that transforms general electronic reliability engineering into true functional safety engineering focused on mitigating specific hazardous events. It tells engineers fundamentally, this is how critically important this function is, and therefore this is how bulletproof this piece of hardware needs to be.
All this incredible detail in Part 5, this intense focus on safety mechanisms, diagnostic coverage, those quantitative metrics, SPSM, LFM, PMHF, what's the ultimate goal of all that immense effort? It's clearly a lot of work.
It is a lot of work, absolutely. But it's all geared towards one overarching, non-negotiable objective: systematically identifying potential random hardware failures, analyzing their effects, mitigating their risks through design and safety mechanisms, and then proving, with objective evidence, that the remaining residual risk from these unpredictable random hardware failures is sufficiently low. Back to sufficiently low, and demonstrating it rigorously. This detailed, data-driven, analysis-intensive, and intensely rigorous approach, mandated by ISO 26262-Part 5, is precisely what provides the necessary confidence for engineers, for manufacturers, for regulators, and ultimately for you, the driver in the safety of the increasingly complex electrical and electronic systems proliferating in our vehicles. It's the systematic process that aims to turn hoping something is safe into knowing it is safe, backed by a mountain of documented evidence. It really makes you appreciate that even though software often gets all the spotlight in modern vehicles, given how many millions of lines of code they contain,
it's truly the robust, meticulously designed, analyzed, and thoroughly tested hardware developed according to standards like Part 5 that forms the indispensable bedrock for overall functional safety.
Absolutely. You said it perfectly. Without that incredibly strong, reliable, and fault-tolerant hardware foundation, that silent guardian constantly monitoring itself and its surroundings, ready to react safely to failures, even the most perfectly written and verified software cannot ensure safety when physical components inevitably degrade or fail randomly over time. The hardware is truly the unsung hero of automotive functional safety, built with an astonishing level of foresight, diligence, and engineering dedication driven by this standard.
And there you have it. We've journeyed through the meticulous, demanding, but ultimately reassuring world of ISO26262-Part 5, product development at the hardware level. We've uncovered how every transistor, every resistor, every connector, every wire is considered in the grand scheme of automotive functional safety.
Yeah, from defining those precise safety requirements and designing resilient architectures to quantitatively evaluating the probabilities of failure using metrics like SPFM, LFM, and PMHF, and finally subjecting the components and the integrated system to extreme tests. It's a remarkably rigorous process.
All driven by that ultimate goal of protecting vehicle occupants and others on the road.
Exactly. And perhaps to leave you with a final thought, as vehicles become increasingly automated, increasingly complex and interconnected, and as new hardware technologies like advanced AI chips, new types of sensors, or even different semiconductor materials emerge at an ever-accelerating pace, it raises a really important question for the industry. How might the automotive industry adapt these deeply thorough, highly effective, yet traditionally quite time-consuming hardware development and verification processes described in ISO 26262 to meet the demands of much more agile innovation cycles? How can we ensure that functional safety keeps pace with rapid technological advancement without ever compromising on that unwavering fundamental commitment to safety? What challenges, but also what opportunities do you foresee in this constantly evolving landscape for safe automotive hardware?